Okay, now, in fact, some of you have seen, well, a couple of my talks before, maybe 2 or 3 before, in particular this one. But, you know, there's some graduate students in the audience and so on, and I'd like to set the general scene. So this is a very introductory problem, and I'll just sort of mention 2 topics now in this introductory talk, which I'll take up in the next couple of lectures, and then the 4th and 5th lectures I'll get on to something a bit more interesting, perhaps. Okay, so, right, so this is an introductory talk, and so first there's some motivation. Okay, and firstly there's some motivation for physics. I should say right away that these talks, these slides are on my website. So just, you know, Google knows where I live, and Google knows my website and all that sort of thing, so you can just go to my website and find these talks. The only thing is you've got to go to the Australian National University website. So I think if you put my name straight into Google with no additional information, you'll get, first of all, me in Adelaide, and second of all, a very famous hockey player. But then, but if you add Australian National University, you'll find me and these slides. Okay, so motivation from physics. Okay, so the first thing is that from general relativity, there's a geometrical motivation without any differential equations at all. Well, not many differential equations, that the so-called null geodesics are conformally invariant. So let me just explain that. And then I'll explain also that Maxwell's equations are conformally invariant. So these are actually 2 systems of partial differential equations which somehow only see the conformal structure. The first one there is in a general manifold. So the setting is you have a metric on M. All my metrics are called G. I always use indices to write everything out, so you can think of this in local coordinates if you like. So GAB is just my metric written in some local coordinates. But in fact, for null geodesics, you really need a pseudometric. So let's have a pseudometric instead of a metric. What I really have in mind, of course, is a Lorentzian metric for general relativity. Let me just explain without any differential equations at all why the null geodesics, these are the geodesics which are everywhere null, why that concept is conformally invariant. You can do that without any differential equations at all, really. First of all, there's this sort of operational notion of what conformal invariance means. And a conformal manifold is one where you've got not really just the metric, but you've got a class of metrics. And the metrics are related in this way, that this one here is supposed to be in the same conformal class as this one, if and only if it's a scalar multiple. And I choose to write my scalar multiple here. It's a positive function. I choose to write it as a square of a smooth function. That's so that things have the right sort of units of length. So this thing here has units of the inverse of length or something. Anyway, but this is my definition of what conformally related metrics are. And I want to convince you that if I look at null geodesics, it doesn't actually see this change. These are just as curves, not as parameterized curves. The way to do that is to think of the square of the metric, in order to make it smooth, as a function on the cotangent bundle. So just think of it as a smooth function, but defined on this bundle. It's a real valued function, positive real valued function. And if you do that, then there's a slick way of writing down what the geodesics are in terms of symplectic geometry. So on T star M, you have a symplectic form, and you use that as follows. First of all, you just differentiate this function. So that literally means the one form, which is the derivative of g squared. And from that, using the symplectic form, you get a vector field. So you've got a non-degenerate skew form on the tangent bundle to the cotangent bundle, so you can swap between vector fields and differential forms. So I do that, and I get myself a vector field, and And then if you look at the integral curves of that vector field, you get what's called the geodesic spray. So you get a foliation on T star M, which you can then push down into your manifold and get yourself geodesics. So that's a quick way of saying what geodesics are without sort of getting into the Levi-Civita connection or something like that. Okay, but this point of view also shows you that this notion is invariant if you rescale the metric. So let's just do that. So suppose I now replace my function g hat by this new function omega squared. Replace the function g squared by omega squared times g squared. So that's a new function on the cotangent bundle. And when you differentiate that by the chain rule, you get two components. So you get just something which is just the original thing scaled. And then you get something which, or the important thing here is it has a factor of the metric out the front. So if you restrict to where the metric is 0, so let's do that. So now restrict the corresponding vector field to where the metric is equal to 0, you get something which is simply proportional to the original vector field. So in other words, this term drops out and you only have that term. And so the result is that your vector field is scaled in some way, but at least the integral curves are the same curves. Okay, that's the end of it. Okay, I'm not going to do anything else with symplectic geometry or anything, so if you didn't follow that, that's okay, we'll start again now. Okay, now let's look at why Maxwell's equations are conformally invariant. Okay, this is a sort of different kettle of fish, really. The point is that if you have a metric on the manifold, it doesn't have to be a pseudo-metric anymore, this is a genuine metric, then you get a volume form associated with that, at least if your manifold is oriented, which I'm assuming and suppressing. So, for example, you can just normalize pick any volume form, okay, that's unique up to scale, and then normalize it so that this happens. That's my favorite normalization. So here I'm adopting some of the standard conventions from Riemannian differential geometry, where if I write something with indices up like that, as opposed to my original volume form, which had all its indices down, then I'm raising the indices with respect to the metric. So this is a fundamental invariant thing you do on a Riemannian manifold. Okay, and then you ask, how does this volume form change if you change the metric? So many of these questions in conformal differential geometry are sort of operational questions. You write something down, which makes perfect sense in the Riemannian setting. You change the metric and you see what happens. So let's do that here. And you can easily check this thing here scales, the one with its indices up scales. And you can check that what happens is that if you scale the metric by omega squared like that, then the volume form rescales by omega to the n. Okay. As I was saying, this omega here is has the units of length. So volume has the units of the dimension of the manifold. So in any case, this is a simple check. And in particular, if I take, when n is equal to 4, let's now specifically take n equal to 4, and raise two of the indices here, then you'll find that epsilon itself scales by omega to the 4. Raising a couple of indices there, you've used the inverse metric twice. That scales by omega to the -2 twice, and everything cancels out. And you get this gadget here, which is then invariant. And how are you to think of this? Well, you think of this thing as a mapping on two forms. So this is taking two forms here. So this is something with skew indices. That's a two form. Okay, to another two form by using this endomorphism on two forms. Okay, so all of these things have names. This is the Hodge-Star operator. And the point is that this thing here in 4 dimensions, specifically in 4 dimensions, is invariant. And so, as a pair of conditions on F, you could require that F be closed, and also that star of F be closed, and that would not see the metric. So these two conditions here are requiring that F be closed. So here I'm just writing everything out without indices on. So this is F is closed and co-closed. That pair of equations is invariant. These are called Maxwell's equations in vacuum. Whoops, these are called Maxwell's equations in vacuum. Oh, I thought I had another piece there which said, well, I can't really. It's so if I put, this is Maxwell's equations here, it would actually go off the page. So, okay, so, right, these are Maxwell's equations. They are conformally invariant. Right. So that's the motivation from physics, a couple of very simple things which are conformally invariant. And basically, anything to do with, like, the speed of light or propagation of light, both of these things have to do with light or electromagnetism. Things like that, massless field equations, and so on and so forth. All of these things are conformally invariant. Okay, so now some motivation from geometry. Okay, so motivation from geometry is that where you start with the sphere and you look at stereographic projection. Okay, what does that mean? You sit the sphere on top of Rn like that. You put a light source at the top. There's a sun at the North Pole. You look at the shadow that casts on the plane. That defines your mapping from the sphere to the plane. Defines a map of the sphere everywhere apart from the pole, the light source. And I claim that that actually preserves angles. That is a conformal mapping. Okay, what I mean by that is if I take the normal round metric on the sphere and I compare that with the flat metric on the plane, the two metrics that we have naturally associated with these structures, then this is actually a conformal mapping. Okay, there's one proof in this lecture. It's this. So I'm going to prove that this thing's conformal. Okay, this is a picture of why this is conformal. So here's a side view. These are actually spheres. They've come out as sort of ellipses here, but you have to... Anyway, this is a sphere in the original PDF file. And, right, and here's a picture of this side on. What you should imagine in order to try and see that angles on the sphere are going to be faithfully reproduced as angles down on the plane is that you're supposed to think of this thing and see how it intersects. Well, you're supposed to look at this line and see how it intersects. First of all, the plane, which is the plane on which it's sitting, and second of all, the tangent plane, which is here. And in order to think of these things, in order to think of how angles are transferred from one of these planes to the other, you should think of this yellow line here as the base of a trough. Okay, this is one thing that sort of animals feed out of. Okay, so this is something like that, and you're going to stand on the sphere and put a trough with whose I don't know there's probably a technical farming term for the line that goes along the bottom of the trough. Anyway, so this is the line which goes along the bottom of the trough here, and you're supposed to see how the trough intersects with this plane and this plane, because the way the trough intersects with those two planes is precisely how angles are measured, both down on that plane and up on that plane. Okay, because after all, the round metric on the sphere is simply inherited from the ambient metric here in, well, as I've drawn it in R3. So I'm thinking of all this in R3. Okay, so there n was general. But this is, if you like, start by slicing that top picture by R3 in order to have something we can draw. All right, yes? Is it possible to sketch the trough picture on... I can draw a trough, yes, okay. We'll try, yeah. Okay, so a trough looks like this. Let's do that. Okay. So it's just the intersection of two planes, but since we're in an agricultural state, whoops, that's a dotted line, yeah, down the back here. Right, this is a trough, but there's no particular orientation to this trough. It's just any old trough you like. So right, so the correct order of events is I take a couple of tangent vectors here on this plane, and I want to see that what happens to those tangent vectors is that when I push them into the plane. So I take the two tangent vectors and I use those two tangent vectors to define the two sides to my trough. Okay, right, and then push it in. Right, now the claim is that there's a symmetry here, and in fact the angle that this thing meets that yellow line is the same as the angle that this meets that horizontal line. Okay, and then that will be a complete proof by symmetry. Right, so everything would then be symmetrical, about a mirror, which is inserted here. Okay, now in order to see that, there's one more construction line that you have to put in. So I put in this construction line here. Okay, and now the proof is like this. What you want to see is that this angle here is equal to that angle there. Okay, well, that angle there is certainly equal to that angle there. This angle here is equal to that angle there, because this and that top line are parallel. And then this angle here is equal to that angle there by symmetry. Right, so this is any point you like, and what you've done is put in a tangent line and another tangent line to the sphere. And it's symmetrical about an axis like that. Okay, end of proof. Okay, that's the only proof. Right, so alternatively, of course, if you're, don't like geometrical pictures or stuff, you just write down the formula and check that it's conformal. Okay, here's the formula, so you can check it. So that's the sort of more pedestrian approach. Okay, so that's the motivation from geometry, and well, let's have some final motivation is from navigation. This is how these things were first came about. The Mercator projection. So Mercator was a sort of experimental cartographer. He didn't actually go anywhere and meet maps. He met sailors, and sailors would tell him what was out there, and he'd draw maps. But what he did was, well, he didn't draw this one but this is a sort of what is now a standard projection of the sphere. And of course, geometrically, it's rubbish, right? Because it's got Greenland here is a little bit bigger than Australia, and that's not actually true. So Australia is quite big, and Antarctica here looks like it's massive, which is true, but not that massive. So, but angles are preserved. Now, why is that? Well, that was actually justified by Wright as a mathematician. He's a mathematician in 1599, so some years later. And from the point of view of the previous slide, you can just see it, because what you can first do is do stereographic projection. That's certainly conformal. We just decided that by geometry. Then you can identify the real plane with the complex plane, like that. And then you can take logarithm. And I claim that logarithm is another conformal mapping, so you can just compose these two things. And the point is that if you look at a general mapping from the plane to the plane, written in terms of coordinates, say u and v and x and y, and look at the Jacobian like that, then to be conformal is to say that the Jacobian has that form, which is precisely the Cauchy-Riemann equations or the anti-Cauchy-Riemann equations. So basically, it's because this is a holomorphic function that this is a conformal mapping. It's a composition of conformal mappings. This gives you the Mercator projection. It's actually the first sort of serious use of a transcendental mapping in sort of real life, right? Because logarithm is involved. Okay, right. So that's the end of the motivation. And now let's look at some symmetries. So as a warm-up exercise, we'll think about Euclidean symmetries. So these are just symmetries of Euclidean space, say symmetries of the Euclidean plane. Suppose you did not know what all of the symmetries of the Euclidean plane are. I mean, I know that you do. They're translations and rotations, right? But suppose you try and just figure that out from scratch. Okay, well, what you could do is take a vector field. There's my notation for a vector field. These are the usual coordinates on Rn. And I'm going to write it like, so, you know, this is the flat connection on Rn, if you like. Okay, I'm going to write it like that as xa, and then an infinitesimal Euclidean symmetry is simply saying that if you look at the Lie derivative of, with respect to this vector field of, well, delta AB as the flat metric on Rn, then it should be 0. That's an infinitesimal statement that you have a vector field which is a symmetry. Okay, so let's first of all figure out what that means as a condition on x. This is a condition on x. So, well, if you compute, this is what the Lie derivative means with respect to any connection. And if you use the Levi-Civita connection, you get that, because the first term here drops out. And because I'm allowed to move this past there, I can lower the indices and so on. And so what you get is that it turns out that this condition, which is a nice geometric condition, turns into precisely this condition. Okay, so this has a name. This is called the equation of a killing field. All right, so here you've got a vector field, which I've just written out in components. And this notation here, these round brackets here, mean take the symmetric part. Okay, so what you could do for any vector field, or I've lowered the indices here, so for any one form, you could look at this derivative, this system of derivatives. That will be an n by n matrix, and it naturally breaks up into its skew part and its symmetric part. If you require that the symmetric part be 0, then this is the equation of a killing field. If you require the other part be 0, if you require the skew part be 0, that's the same as saying that X is closed as a one form. Okay, so this is like the other natural equation you can write down in one form. So this is a killing field. And what I'd like to describe now is how you solve these equations. Right, so these are a system of partial differential equations on Rn. This is a bit of a theme. This will come back in later lectures. Okay, well, what you do is, so I want to try and decide what the solutions to this equation are. This is done by what's called prolongation. It's a fairly standard technique. So, but for this particular operator, it's straightforward as follows. What you do is you rewrite, what you're interested in is the kernel, so the solution space. You rewrite this by saying if you look at the matrix of all derivatives and call that K, then to say that the symmetric part is 0 is the same as saying that the matrix of all derivatives is skew. Okay, so this is nothing's happened now. The wheels are spinning. All I've done is introduce a name for the derivatives and re-articulated the conformal killing equation by saying that this matrix should be skew. Okay, now, I claim that when you do that, then the derivatives of K, so that these things are all functions on Rn, the derivatives of K have to be 0. Okay, now why is that? Well, this is certainly true. What I've done here is just write out the statement, the K, which is a skew two form, so it's really a two form. What I've done is written out with indices the statement that because K is actually the exterior derivative of something, it had better be closed. Okay, so, but I mean, nevertheless, this is just an elementary consequence of the equality of mixed partial derivatives. Okay, so then, in order to establish this claim, you take this identity here and you plug back in what K actually is from here. Okay, so that's what I've done to get to the next line. But then mixed partial derivatives commute, and so you get 0, right? So here I've got exactly the same expression as here, except the indices B and C are in the other order, right? So because these are derivatives, this is a symmetric matrix. This equals 0 as required. Okay, so when you do that, you assemble all that together, then what you've done is rewritten your original equation here as a series of equations where you know all of the derivatives of all of the things involved. In other words, what you've got is a so-called closed system. Okay, so in the general procedure of prolongation, what you do is you introduce symbols for the derivatives you don't know. So like here we knew that the symmetric part was equal to 0, so we introduce a name for the other part. And then you deduce differential consequences and try and work out what all of the derivatives of all of the things that you've introduced actually are. Okay, so you get this is closed. And the conclusion is that then you can solve this because, well, this thing here has to be constant, so K has to be constant. And then you substitute back in here and you deduce what X is. Okay, so and here's the general solution. And of course, these are the infinitesimal notion of translation. So when you plug this back into being the vector field, these are your infinitesimal translations, and these are infinitesimal rotations. Okay, so that's a warm-up exercise to figure out what what we all know, which is on Rn, the symmetries are translations and rotations. All right, now let's try this for conformal symmetries, and you see that something slightly different will happen. And it will actually introduce one of the, well, okay, let's just do it. Let's see what happens. Okay, conformal symmetries, well, if you write out what that means, it's actually that the trace-free part should be equal to 0 rather than the entire symmetric part should be equal to 0. So the trace-free part of the symmetric part should be equal to 0. Right, that's a conformal killing field. Okay, you can just take my word for it, but this is the sort of natural thing that you would expect. Okay, so when you rewrite it, you've got a k as before, but then you've got something which is just a multiple of the metric. Okay, that's exactly just rewriting what the conformal killing equation actually is. So let's do that. As before, k would be closed. So this is exactly what I'm doing before. But then when you substitute back in here, you find that you get lambda coming into your equation. So you do that. So this is just plug and chug, right? I'm just substituting back in from the original equation. You get what I had before, which are these two terms. And then you get some extra terms. Right, the two terms that cancelled before still cancel. And now I'm just going to introduce a name for the final derivative that I don't know, which is this. So I'm going to introduce a name for the derivative of capital lambda and call that, well, minus q. Right, and then when you do that, differentiate some more. Right, this is the standard theme. You differentiate some more. Look at some part of what you've got and re-express it, blah, 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 blah. Okay, then what happens is that, well, what happens is that the number n minus 2 arises. Okay, so just go through this. This is just some trivial tensor algebra, but notice that the number n minus 2 happens. When n is equal to 2, these equations don't tell you so much. When n is greater than or equal to 3, then it actually tells you that the derivative of q has to be 0. Okay, so there's a distinction between n greater than or equal to 3 and n equals 2. And this is an important distinction. So for the rest of the lectures, I'm talking about conformal geometry in dimension greater than or equal to 3. Conformal geometry in dimension 2 is Riemann surfaces, and they're sort of locally floppy, whereas conformal geometry is different. It's sort of rigid in the same way that Euclidean geometry is rigid. Okay, so now look at these yellow boxes here. So this one, this one, this one, and this one. This is a closed system now. Right, so all of the yellow boxes are a closed system, and you can reconstruct what the symmetries are. So let me do it. Also, on this page here, what I've done is just assemble those 4 equations into a big yellow box like this, and you can solve them. So, for example, this one here says that q had better be constant. There it is. And then you substitute back, substitute back, substitute back again, and you deduce that this is what you get for your vector field. So this is a general conformal symmetry. All right? And you recognize some of the components that you had before. You have translation, that's this. Just so that's a Euclidean symmetry, certainly a conformal symmetry. You have rotation, that's this skew m here. Then you've got a new one controlled by lambda, that's an infinitesimal version of dilation. And then there's this new, really nice exotic one here controlled by r. And these are actually inversions. And even if you didn't know about inversions, you could reconstruct them from this because what you could do is just set S and M and lambda equal to 0 and integrate these vector fields. Okay, so if you integrate them, this is what you get. So here is a transformation from Rn to Rn, which preserves the conformal structure. And I mean, the conclusion of all this is that these are the general fields which do this. There are no more, at least infinitesimally, you cannot do better. Okay, so this you can just get by solving some ODEs. Okay, so that's what you get if you just. But notice that of course these vector fields are only defined where the denominator doesn't vanish. So there's some places where these vector fields screw up. So in order to introduce the group which is acting here, you have to fix this problem. You have to fix the problem that some of these vector fields are not defined everywhere. And that's what's happening on the next slide. This is the conformal group. Okay, the point is that, well, I'll just tell you right away what the group actually is. It's SOM plus 1, 1. It's acting on the sphere. So this group acts by conformal transformations. Okay, so I'm not going to prove that, but you can see that it at least has the right dimension and so on and so forth. The picture is like this. SOM plus 1, 1 is acting in Rn plus 2, and it preserves the light cone. Right, so there, this is the Lorentzian group. It preserves the light cone. There it is. And you can see the sphere in this picture. It's actually the space of generators. Okay, so these red lines here are the forward light cone, the forward light rays, future-pointing light rays. Okay, and they at least, well, you can identify them with a particular slice if you like. You know, identify them with this particular copy of Sn. But you shouldn't do that. You should regard the space of generators as being the sphere. Okay, any particular slice will give you a Euclidean metric. Okay, and but the point is that this is what you might call the most sort of symmetrical model of conformal differential geometry. So here you see that you've got a group acting, a very nice classical group, and you've got a subgroup which you can identify explicitly if you want to. You should compare this with what happens in Euclidean space. In Euclidean space, the flat model is, well, it's Rn. The symmetry group is Euclidean symmetries, which is this. So translations and rotations, modulo the stabilizer of a point, which is just SON. You notice there's something actually a bit quite different between these two cases, and this is basically why conformal differential geometry is more complicated than Euclidean differential geometry, and that is that the groups have a different character. So in the Riemannian differential geometry, it's the stabilizer of a point which is semi-simple. Or, well, most of the time it's simple. Here, it's the global symmetry group which is semi-simple. And this subgroup here is one of a very special type. It's called a parabolic subgroup. This is the sort of general features of conformal geometry which actually pertain to in other geometries as well, where you have a semi-simple Lie group modulo a parabolic subgroup. Okay, but you know, almost all of my lectures are just about this particular case. So I'm not going to tell you much about P at the moment. Just a little bit later we'll have to discuss what P looks like. Okay, now here's another motivating question. Okay, so the first question is maybe to understand the invariant differential operators, say Maxwell's equations and so on and so forth. Here is another simple question on Rn, which is going to be one of the topics of my next couple of talks. Okay, so here's the simple question. The simple question is, which linear differential operators on Rn preserve harmonic functions? Okay, so this is a seemingly innocuous question. And you can start answering this sort of by hand. You know, you look at the, well, first of all, what about, well, a linear differential operator? It could be just multiplication by a function, right? That's a zeroth order differential operator. And the answer is that the only way you can multiply a harmonic function and get another one is to multiply it by a constant. You're not allowed to multiply it by any other function. It must be constant locally. Okay, so that's a complete list of the zeroth order differential operators which answer this, which have this property. Okay, we've done that. What about the first order ones? Well, first order ones, there's the infinitesimal generators of translation. Right, so the Laplacian is translation invariant. Okay, so in fact, these operators here just commute. These operators commute with the Laplacian, and that's the infinitesimal version of saying, that's the infinitesimal counterpart of saying that the Laplacian is translation invariant. So these are certainly symmetries. They have the property that harmonic functions are preserved by these operators. There's also operators like this one. Here we're just in R3. So these are the standard coordinates which I've been using before, x1 and x2. This means differentiation with respect to x1. This is the infinitesimal version. This is the infinitesimal generator of rotation about the x3 axis. Okay, and there's three of those. So when I write etc. here, I mean that you can permute these. So you could have x2 d by dx3 and so on. Okay, so there's three possibilities there. Okay, then there's, well, this one doesn't actually commute with the Laplacian, but it behaves well with respect to the Laplacian. This is the Euler operator, and this is the infinitesimal version of dilation. Okay, and then there's some rather more complicated looking ones. So, but you know, you can get these by hand. This is a perfectly tractable task. You know, apparently having nothing to do with conformal differential geometry at all, and you can check that this one here has the property that if you plug in a harmonic function, you get another harmonic function from it. And apart from the fact that you can permute the indices here, this thing here, I mean, this is not a vector field anymore. At the end here, this is a multiplication operator by this coordinate. Okay, so this is a first-order differential operator, not just a vector field as those other ones were. Okay, but nevertheless, this takes harmonic functions to harmonic functions. And apart from permuting the indices here and permuting the indices there, this is a complete list. Okay. Of course, you can add on the zeroth ones to the first-order ones as well. Okay, now, if you look at the of how many of these things there are, then you might spot that this actually really does have something to do with conformal differential geometry. First of all, there's this zeroth order one. There's just one of those up to scale, so I've put a 1 there. There's three possibilities for the translations, 3 for the rotations, 1 for the dilation, and 3 for these other ones at the end, whatever they are. Okay, and you add these up and you get 10. Okay, not only that, but of course, if you have a couple of symmetries, so let me call these symmetries D1 and D2. So D1 and D2 are just, you know, differential operators, linear differential operators, first order, which send harmonic functions to harmonic functions. If you look at the commutator like that, that's another one, and that will also be first order because the leading order terms will drop out. So this will be another one. So this 11-dimensional space altogether is a Lie algebra. Okay, and you can ask, what Lie algebra is it? And well, let's see. Yeah. In order to what happens is that well, this is a Lie algebra, an 11-dimensional Lie algebra. There's a commutator subalgebra inside it, which is 10-dimensional. And then that 10-dimensional algebra is actually isomorphic to SO41, which is the symmetry algebra for conformal differential geometry in 3 dimensions. Okay? So in order to do that, in order to get that in order for these things here to be a closed 10-dimensional symmetry algebra, actually you have to add in a little bit of this one into here. You have to put a +½ there. Then these differential operators are in fact closed under Lie bracket. Okay, so you just check that, and minus half, this half here plus a half here is a significant number as regards to the Laplacian. Okay, so this is the story, and in not the next lecture, but the lecture after, so the one tomorrow, I'm going to sort of explain what this has got to do with conformal differential geometry. You see that it should have something to do because of you getting the right symmetry group coming out. So somehow this is another motivation for conformal differential geometry, just coming out of harmonic functions and nothing else. Right, so this is a shock horror. It's the conformal algebra. Why is this? Okay, so let's see. Just by way of a sort of advertising poster, this is what conformal geometry has to do with. These are the surroundings of conformal differential geometry in the mathematical landscape. So I'm only going to talk about little tiny bits of this, of course, because this is a big landscape. So here it is, very close relationship between conformal geometry and CR geometry. So if you like CR geometry, you will like conformal geometry, and vice versa. So CR geometry has as its flat model a semisimple Lie group modulo a parabolic subgroup. So these are two things which can be unified. there's lots of other stuff flying around here. The stuff on the right-hand side of this diagram is sort of from physics and analysis. These sorts of things. The stuff on the left-hand side here is more to do with algebra and geometry. So the title of this series is something to do with representation theory. The last talk I'm going to give is about integral geometry. The fourth talk I'm going to give is about twistor theory, and so on and so forth. This terminology here, parabolic geometry, that's the geometry of spaces which are modeled on semisimple modulo parabolic subgroup. So that's a big topic in itself. I'm going to talk a little bit about BGG machinery this afternoon, and so on. Okay, so the point is that if you recognize any of the words on this slide, this is supposed to make you feel warm and happy. All right, but for the next three talks, this is what I'm going to talk about. So next four talks, yes, okay. Getting confused here. So this afternoon I'm going to talk about, what are these, what about conformally invariant operators more generally? So not just Maxwell's equations, which are kind of simple. I want to talk about something a bit more meaty. Okay, and so we're going to discuss them, maybe even classify them. That would be nice. The question that I was talking about with differential operators preserving the Laplacian, right? I was talking about first order ones. What happens beyond first order? That's the topic of the next talk. After that, the fourth talk is about twistor theory. Okay, and something called Bateman's formula, which is a really cool formula. Okay, the final one is the final talk is about integral geometry, real integral geometry, in particular the X-ray transform. Okay, and well, here's a couple of further places where you can find stuff about conformal differential geometry. Really, this book here, which is about differential geometry in 4 dimensions, especially using spinors, is really geared up to being conformal differential geometry in 4 dimensions. That's what this one is. And these are my notes on conformal differential geometry from some time ago. Okay, right, so it's about time, isn't it? Okay, so you won't mind if I finish 3 minutes early or something like that. So that's the lot for today. So thank you very much.